I would like to welcome everyone to the NAM Claytor-Woodard lecture. I am Candace Price, currently at Smith College, and I am happy to introduce my friend, Dr. Chelsea Walton, who will be talking to us about an invitation to non-commutative algebra. Just a bit about Chelsea before she gets started. Chelsea Walton is originally from Detroit, and she was educated in the Detroit public school system. Chelsea graduated from Michigan State University in 2005 with her undergraduate degree. She completed her PhD at the University of Michigan in 2011 under the supervision of Toby Stafford, and Karen Smith. Chelsea is well known and has a lot of accolades. I'll just name a few of those right now. Chelsea became the fourth African American to win a Sloan Fellowship in Mathematics in 2017. She's also been recognized by Mathematically Gifted in Black. Just got to put that plug in there. In 2018, Chelsea won the Andre Lichnowitz Prize, words are hard, in Poisson geometry. She's the first woman to be awarded this prize. I think with all of that, let's welcome Chelsea Walton to talk to us about non-commutative algebra.
Wow. Okay. Well, thanks, Candace, for that great introduction. I really appreciate it. And thanks to NAM for inviting me to speak here. It is a true honor. So it's the last day of the JMM, and I am truly thankful to all of you in the audience who are here. I mean, news-wise, it's been an exhausting week, right after an exhausting year. So if you gave a talk this week or listened to a talk or listened to a piece of a talk, give yourself credit for this, please. And I hope that listening to this talk will be worthwhile. So let me entertain you for a little bit, and let's take an adventure into the world of non-commutative algebra. And we don't need to go far to start because the world is non-commutative. Let me try to convince you of this. Doing laundry is non-commutative. I mean, think about it. If you pop your clothes first in the washer and then pop them in the dryer next, you get a completely different result than if you put them in the dryer first and then the washer. Non-commutative. And what about feeding your pets? Well, if you have a greedy pup and a picky pup like I do, then the order in which you feed these creatures matters. Non-commutative. Now, more mathematically, let's consider reflections and rotations. And as you can see here, whatever TV show I'm watching tends to make it into my talk. So let's take this image here, this little green creature, and rotate by 90 degrees clockwise, and then reflect horizontally. This produces a different result than first reflecting horizontally and then rotating 90 degrees clockwise. So the world is non-commutative simply because the order in which we do things or the order in which we perform functions matters. Now, let's dig into why taking reflections and rotations or compositions of is a non-commutative process using matrices. So to start, let's take this little green creature, and embed it into real two space. And we want to do this so that we can keep track of rotations and reflections using coordinates. Now, let's pick a basis of R2, the standard 1, 1, 0, 0, 1, and let's see where these basis elements go under these transformations. So for instance, I can send the first basis element 1, 0, by 90 degrees clockwise rotation, it goes to 0, negative 1. And then the second basis element, well, that gets sent to 1, 0. And using that information, I could write down a matrix corresponding to that transformation. Likewise, the matrix corresponding to the reflection transformation is this matrix, just by seeing where the basis elements go. All right, so conveniently, the matrix corresponding to a composition of transformations, this is determined by matrix multiplication, which we all love to do, yeah? So for example, if I were to first rotate and then reflect, I can write down my rotation matrix here, my reflection matrix here, take their product, and this matrix represents this composition. And I have to do the matrices in this order because of the way composition works. On the other hand, if I write down the matrix corresponding to this composition, I end up with this matrix. Now, as we can see here, the two products, they're not the same. So this gives us a mathematical reason why composing functions is non-commutative. Let's nail down the actual algebraic structure that's at play here, the one that we're going to use throughout this whole talk. Okay. Go. All right. So let's review some algebraic structures. First, let's start with a monoid. Now, a monoid is just a set that has an associative binary operation called addition, and also an additive identity, which we usually call 0. Now, if we also have additive inverses, then we get what's called a group. And if the operation is commutative, then we have an abelian group. Now, with an abelian group, we can build two types of algebraic structures, rings and modules. And basically, the algebraic structure that we're going to use throughout this whole talk is a combination of a ring and a module called an algebra. So what is a ring? A ring is an abelian group that has an additional binary operation called multiplication. It's associative, but not necessarily commutative. Now, if you have a ring that also has an identity element with respect to this multiplication, we call the ring unital or ring with unity. And if we also have multiplicative inverses, then we have a field. On the other hand, let's take an abelian group and build a module from it. Now, to do this, we're not going to multiply elements of the abelian group like we did in a ring. Instead, what we have is a scalar multiplication. So what you have is a base ring R, and you take an element of your ring R and an element of your abelian group, and you combine them to get an element of the abelian group. Now, a lot of us have seen modules before. In particular, if your ring is a field, then what you get is a vector space. Many of us have seen vector spaces. And in fact, the algebraic structure that we're really going to use in this talk is going to be a combination of a ring and a vector space, i.e. an algebra over a field. And usually for us, the multiplication is going to be non-commutative. Let's see some examples of algebras over fields. Okay, I'm going to do it like that. All right. Okay, so building on the examples that we were using before, let's consider a collection of matrices. Now here, the collection of matrices forms an algebra with the three operations that you expect: matrix addition, matrix multiplication, and scalar multiplication. On the other hand, we can take an algebra that's related to the matrix algebra, the so-called endomorphism algebra. In particular, these are related because matrices encode linear transformations from a vector space to itself. So for instance, if I take the vector space R2, then any linear operator on it corresponds to a 2x2 matrix with real entries. Now, this collection of endomorphisms of R2, this forms an algebra over the real field with component-wise addition, component-wise scalar multiplication, and the multiplication now is given by composition, composing these linear transformations. Now, both of these algebras here, they're quite nice. I mean, they're nice because they're non-commutative, but they're also nice because they're actually isomorphic to one another as algebras. By that, I mean as rings and as our vector spaces. So now let's touch upon some themes that we're going to see in this talk over and over and over again, some themes in non-commutative algebra. There are 3 of them. And the first one is representation theory. This is all about finding matrix solutions to equations. That's basically what the field is. And in particular, non-commutative algebras, they arise when finding solutions to equations and non-commuting variables. Now, this was motivated by problems in quantum physics. And these days, really nice algebraic, geometric, and even combinatorial tools are used in modern representation theory. The next theme in non-commutative algebra that we'll see is the theory of deformations. Now, this is all about altering structures slightly, leaving some parts of the structure alone while perturbing other characteristics. Now, one interesting area of study is to deform algebras themselves. Now, by this, I mean, we're going to leave the vector space structure alone, but we're going to change the multiplication of the algebra, change the ring structure a bit. Origins of this game, they lie in geometry, topology, and some really useful algebraic tools have been developed to study such problems, like tools in homological algebra, even some tools in category theory. Now, the last theme that I'll highlight in this talk is the theory of symmetries. And this happens to be my favorite, hands down. I really like it. Symmetry is an old concept. It appears all over the place, art, music, anywhere where there's patterns. But mathematically, a symmetry is basically a transformation from an object to itself, as was beautifully discussed in Amy Wilkinson's talk on Wednesday. So where do noncommutative algebras come in? They come into play when we start to study symmetries of quantum objects, whatever these are. Now, in order to understand this, we really need to use a bit of deformation theory, maybe some representation theory to illustrate this here. So I'm going to share 3 cool stories about representations, deformations, and symmetries later. But before we continue, I would like to point out some really cool people who work in noncommutative algebra, especially in areas related to our 3 themes. All right, lots of people. So in no particular order, we have Floyd Williams, who's an emeritus professor at UMass Amherst. He's written over 85 articles and 3 books in Lie theory in various topics in math physics. Next, we have Kunda Gambaso, who's a grad student in Aachen, Germany. Her first article, a solo paper in representation theory, this appeared on the archive last summer, and I'm sure it's the first of many. Next, we have my buddy and math cousin of sorts, Chris Negron, who's a faculty member at the University of North Carolina. He's produced about 20 articles with many more to come, and I'll highlight some of his work on deformation theory later. Next, we have Ulrika Wilson, who I met while working with the EDGE program a few years ago. And I think she's brilliant. I mean, everybody who knows her thinks the same. She's a faculty member at Morehouse and also a director at ICERN. Her expertise includes division algebras or noncommutative fields. On a related note, Danny Krashen is also an expert on division algebras and in the intersection between noncommutative algebra and number theory. Really cool intersection. He's a faculty member at Rutgers and is published in top-notch journals such as Aviciones and Advances in Mathematics. Next, we have Mboye Osele, who is a faculty member at Northeastern, specializing in math physics, especially string theory. He was named a Next Einstein Fellow in 2017. And he's also the founder of COVID-19 DRC, which is a group of African scientists using modeling to fight the ongoing pandemic. Next, we have Yariana Diaz, who is a new grad student of one of my collaborators, Ryan Kenser, at the University of Iowa. And even though we haven't met yet, I very much look forward to seeing what she gets into, particularly if it's symmetries, especially if it's symmetries. Next, we have Alfred Noel, who's a faculty member at UMass Boston. He's an expert in the representation theory of Lie groups. He's written several articles on nilpotent orbits in particular. And these are really cool Lie theoretic analogs of nilpotent matrices. Next, we have Alicia Lima, who is a new grad student at the Perimeter Institute and the University of Chicago. She already has 3 articles out, and the last one was just posted last month with co-author Matilda McCauley. She's another one to watch. We now have Don King, who is an emeritus professor at Northeastern University. He specializes in Lie theory. And he's published in prestigious journals such as the American Journal of Math and Transactions of the AMS. He was also Alfred Noel's PhD advisor. And lastly, we have some party crasher here with Miriam Muhammad on the left and Angela Tiberi on the right. Miriam is a grad student at TU Dresden, Germany, and so I suspect there'll be some cool results on symmetries in the works. And Angela is an awesome postdoc at Ames, Ghana. She's also Miriam's math sister and one of my collaborators. I'll chat about work with Angela later. Okay, so let's start our stories, and we'll begin the stories with representation theory. Let's start there. So, representation theory, this story starts about 100 years ago at the birth of quantum mechanics, especially with Heisenberg's uncertainty principle. So, Werner Heisenberg was a key figure in the launch of quantum mechanics in the mid 1920s. He was interested in studying the behavior of subatomic particles, and while observing their position and momentum in particular, he noted that the more precisely the position is determined, the less precisely the momentum is known, and vice versa. This statement is now known as Heisenberg's uncertainty principle. Now, mathematically, the behavior or the bookkeeping of this behavior, this was really captured by matrices, which wasn't really comfortably in the physicist's toolkit at that time. In any case, the uncertainty principle yielded the so-called fundamental equation of quantum mechanics. Now, it states that given a position matrix P and a momentum matrix Q, their commutator PQ minus QP, this is equal to a non-zero scalar multiple of the identity matrix. And so enters noncommutativity. It's in the picture now. Now, without loss of generality, we can rescale these matrices in order to get an equation of equal interest, the normalized fundamental equation, just by setting the right-hand side equal to the identity matrix. Now, once we do that, we can start to use noncommutative algebra to find solutions to this equation. And to do so, we need to consider an algebra called the first Vial algebra. Now, this is an algebra, say, of the complex field, generated by two non-commuting variables, x and y, subject to the relation that the commutator of y and x is equal to 1. That means that you take the free algebra, it consists of linear combinations of words in x and y. And every time you see a yx, you're allowed to swap that out with xy plus 1. So the Vowel algebra, it's a noncommutative algebra, it has noncommutative multiplication, but it's also infinite dimensional as a complex vector space. And I mean, you should think about what the basis elements are. Now, we have a really, really nice noncommutative algebra. And in order to illustrate how to use it to find solutions to this normalized fundamental equation, I have to tell you what a representation is. All right, so a representation of an algebra, this is just a module. I mean, so much so that folks use these terms interchangeably, representations and modules, hand in hand. Let's go through this. Suppose that you're given an algebra A. In other words, it's a ring that has a compatible vector space structure. Well, a representation of A, your algebra A, this is a vector space V that comes equipped with an algebra map going from A to the endomorphism algebra on V. We've seen this endomorphism algebra before. Now remember, in V, this consists of linear operators on V, linear maps from V to itself, that has component-wise addition, component-wise scalar multiplication, with the multiplication given by composition. So A is an algebra and NV is an algebra, and we want an algebra map between these two structures. That is, we want a map that is a ring homomorphism that's simultaneously a linear map. So that's a representation. On the other hand, a module over A, it's a vector space, right? And instead of having this map rho, this algebra map, we have an action map. Now what this does is this takes an element of A, an element of V, and spits out an element of V. And this action map star, it has to be compatible with the operations of A and N of V as well. So as you can see here, we can go back and forth between representations and modules. Okay, now we keep the vector space structure alone, leave that alone. But if we have this algebra map rho, we can produce an action map star as given in green here. On the other hand, if you have an action map star, we can produce an algebra map rho as given in purple here. Also, if we would like to keep track of the size of a representation, then all we need to do is take the dimension of the underlying vector space V. So that's called the dimension of the representation. All right, so now back to our normalized fundamental equation. We can see that producing solutions to this equation is the same thing as producing representations of our Vial algebra or modules over our Vial algebra. So for instance, if I take two matrices P and Q, I can produce a representation of the Vial algebra. So for instance, X, that gets sent to the linear operator on Cn given by the matrix Q. Again, linear operators and matrices go hand in hand. Likewise, Y gets sent to the linear operator on Cn given by P. All right, so we get a representation. On the other hand, if we're given a representation of our Vial algebra, say with X being sent to the linear operator determined by Mx and Y being sent to the linear operator determined by My, then we get a solution to the normalized fundamental equation by setting P and Q equal to these matrices, like so. All right, so what about those solutions? I mean, should we try to find some? Should you pause the video and try to compute some 2x2 matrices, 3x3 matrices? Okay, I said pause the video, you're watching this live, but if you're not watching this live, don't do it, okay? Don't try to find solutions. Let me save you some time because at least for finite dimensional solutions, there are not any. There are no finite dimensional solutions to the normalized fundamental equation. Or equivalently, the first Vial algebra, it doesn't have any finite dimensional representations. The proof of this statement is actually quite short. I like it. If you type it out, it will take you 2 lines. So let's go through it. Let's assume, by way of contradiction, that there are some finite dimensional solutions to this equation. Let's say they have dimension n, right? So I take two matrices P and Q, n by n matrices, so that PQ minus QP equals the identity. Now here, n has to be positive. It can't be 0. N has to be positive. So now take trace of this equation. Take trace. On one hand, we get that trace of the identity matrix is equal to n. But on the other hand, we get that trace of the commutator of P and Q is equal to 0. Okay, we get n equal to 0, which is impossible, QED. All right, so no finite dimensional solutions. But there are infinite dimensional ones. There are infinite dimensional ones. I mean, here's one of them, given by these very explicit matrices P and Q here. And in fact, there are loads of solutions to this equation, loads of infinite dimensional representations of the Vial algebra. So much so that whole fields of research were sparked in order to get a handle on this, in order to address, well, that and similar problems in representation theory. So a whole field of noncommutative algebra was launched. For instance, one way to get a handle on the representation theory of the first Vial algebra is to realize it as an algebra of differential operators. So to see this, let's take a polynomial ring in one variable. That's a nice vector space, right? It's an infinite dimensional vector space. And we're going to take linear operators on this vector space. Now, let's take our generator X of our Vial algebra and have it correspond to the linear operator on this vector space given by multiplication by X. That is, I take a polynomial and I multiply it by X. That's how the generator X corresponds to a linear operator. Likewise, let's take my generator Y of my Vial algebra and have it correspond to the linear operator given by derivation with respect to X. So I take a polynomial and I take its derivative with respect to X. Now, one can see that the commutator of these operators, ddx and multiplication by X, this is just the identity operator. And again, if this talk isn't live, I mean, you can pause it and try this for yourself. I mean, take a polynomial and multiply by X and then take its derivative, and then take that original polynomial take its derivative, and then multiply by x, and the difference of the two results will be the original polynomial. This is why the first Vial algebra is considered to be an algebra or ring of differential operators. And its representations fall into this nice family of important representations called D modules, D standing for differential. Now, if you're curious about this, there's a very accessible book on this topic written by Severino Coutinho, who happens to be one of my math brothers. In fact, I borrowed a lot of this narrative here, this story here from that book, so check it out. Now, as we saw, the start of quantum mechanics was also the origin of an area in noncommutative algebra representation theory, but the story is not over, far from over. There are loads of noncommutative algebras and research directions in representation theory that have arisen from quantum physics. Some of the noncommutative algebras and the fields in which they arise appear here. In particular, Lie algebras or enveloping algebras of Lie algebras. These are all over the place. And if you want to know more, check out the work of Floyd Williams, Don King, Alfred Noel. Also check out the work of Mboya Isole for connections between representation theory and string theory. And after the talks are made available online to rewatch online, I highly recommend checking out Jim Gates's talk that was in the adjoint session from this morning. It was a cool talk, so I had to tag this in this morning. All right, so that ends our story and representation theory. Again, I'm just giving you short stories. Just short stories here. All right, so next, let's go to deformation land. Deformation land. Okay, so in order to get this story started, I need to chat about a physical procedure that really prompts the need to deform algebras, quantization. Essentially, this is a process that translates information in information in classical mechanics to the setting of quantum mechanics. And that procedure, this intersects with various fields in mathematics, analysis, geometry, topology, you name it, algebra, quantization intersects with it. So to start with this story, let's say that we have a geometric object or a topological object X that arises on the classical side of this story. In order to proceed with quantization, one typically replaces that object X with its coordinate algebra or function algebra O of X. For instance, instead of working with the complex plane, typically people work with its coordinate algebra, the polynomial ring in two variables. Now, algebraically, quantization is a careful process that alters the commutative multiplication of this classical coordinate ring to get a non-commutative coordinate algebra of some quantum object in the quantum setting. So for instance, if we're interested in a quantized version or a deformed version of the complex plane, we need to work with its non-commutative coordinate algebra or some deformation of the polynomial ring in two variables. So that's why there's a lot of theory built up in deforming algebras. There's a lot. So what is a deformed algebra? I need to tell you what this is. So recall that in algebra, it's a ring that's simultaneously a vector space. In particular, it has three operations: an associative commutative addition, an associative multiplication that could be non-commutative, and a scalar multiplication. So an algebra is a ring that's simultaneously a vector space. Now, deformation of an algebra, this is just, it's another algebra, say, call it like A-def. A-def is going to be equal to A as a vector space, but the multiplication of A and A-def are different in general. So let's go through some examples just to make this clear. Let's deform the polynomial ring in two variables. So, all right, we've already seen an example of this before. The first Vial algebra, that's a deformation. And I'll recall that the first Vial algebra, it has the same generators as the polynomial ring in two variables, x and y. But instead of the commutator of y and x being equal to 0, as it does in a polynomial algebra, the commutator of x and y in the Vial algebra is equal to 1. As a result, any word in the Vial algebra, it can be written as some power of x times some power of y. So as a vector space, the Vial algebra is the same as a polynomial ring in two variables, but their multiplications are different. They have different multiplication rules. So this means that the Vial algebra is a deformation of this polynomial ring. All right, likewise, let's take the Q polynomial algebra, where here yx is equal to qxy, for q a non-zero complex number. Same result, we end up getting that this algebra is equal to the polynomial ring as vector spaces, but you have a different multiplication. Deformation, that's what we want. Now let's take a more interesting example. Let's take the universal enveloping algebra, the Lie algebra SL2. It's generated by three non-commuting variables, E, F, and H, with these three relations set equal to 0. And with these relations, we can see that this enveloping algebra is equal to this as a vector space. These are really not the same vector spaces, so we don't get a deformation of CXY using this algebra. But we do see that this enveloping algebra is a deformation of a polynomial ring in three variables. All right, so here's some nice examples of deformations. Let's kick this up a notch. Why not? Let's go for it. Let's kick this up a notch and work formally. But the purpose of this is always a purpose. The purpose of doing this is to create whole families of deformations, whole families, not just one at a time. So to do this, let's give ourselves an algebra A, F algebra, where F is a field, and let's create a formal deformation of A as follows. Now to do this, we have to work over a power series ring. Okay, got to work over a power series ring. And a formal deformation of A, this is going to be an algebra AT over this power series ring. In particular, it's a module over this power series ring. As a vector space, it's isomorphic to the power series extension of the original algebra A. So this takes care of the module or vector space structure of the algebra. But for the ring structure, well, here's your new multiplication rule down here in blue. We're going to denote the multiplication in this deformation with a star, just to make it different than the multiplication in A. Multiplication in A, I'm going to denote just by concatenation. Multiplication in the deformation, I'm going to denote by star here. All right, so as you can see, it's determined by these maps mu in. These are F linear maps given like so, called multiplication maps. And the 0th one is just multiplication in A. Now, I know this is a bit of a jump, going from this simple definition that we have in the upper left-hand corner to now working over a power series ring. Wah! Before we were just working over a field, that was nice. But we can get from the formal setting to the simple setting by just specializing your indeterminate t at a non-zero scalar. Once you take t and plug in a non-zero scalar, you're back to the easy setting. Let's check out some examples. Okay, so on the left-hand side, I repeated the definition of a deformation, all right? And let's deform the polynomial ring in two variables, all right? And at the end of the day, we're going to get the first Vial algebra. So we're going to create a whole family of deformations, and it's going to specialize to the first Vial algebra. To simplify things, I mean, I really need to write down these multiplication maps, but I'm only going to do it for the generators of A here. Okay, so the generators of A are X and Y, and let's let the first multiplication map of X then Y equal to -1. All right, and let's let the higher multiplication maps of X then Y be equal to 0. So when I take these expressions and I plug that into these formulas, this formula here, I get that X star Y is now equal to XY minus T. Okay, so That gives us at least a piece of the information. Now I need to see what y star x is equal to. So for that, I'm going to just assign all of the multiplication maps of y, then x to all be equal to 0. So in this case, y star x is equal to yx, which is equal to xy. And when I piece this information together, just by taking this expression and plugging it into here, I see that now my relation of my formal Vial algebra is y star x minus x star y minus t equal to 0. It's great. So I have a whole family of deformations. Now, what's cool is that I can set t equal to not any non-zero complex number. Let's say it's equal to 1. And I get a deformation over a field. In this case, the first Vial algebra. All right. Now let's see how we can pick up the Q polynomial ring. Okay, so we're going to play this same game a bit, but now I'm going to set all of my multiplication maps for the pair x then y to be 0. So I have that x star y is equal to xy. But for the pair y then x, okay, I have to be a little trickier. Let's let the nth multiplication map be 1 over n factorial times yx. Now, when I take this expression and I plug it into this formula, the yx factors out. And what I'm left with is the generating function of e to the t. Okay, so what I end up getting is that in this algebra, y star x is equal to e to the t times yx. But that's also equal to e to the t times xy because, well, this is multiplication in A, which is commutative. So piecing this together, I get that in my algebra, my formal algebra, formal deformation, y star x is equal to e to the t times x star y. And by taking t to be log of q, q is a non-zero complex number, I get my Q polynomial algebra. All right, so I think this stuff is kind of fun. But of course, it's not as easy as it seems. I mean, you can't just pick multiplication maps mu of n willy-nilly. You can't just pick them at random to get a deformation. Can't do it. Associativity is an issue. You need this product to be associative. You want an algebra. You want it to be associative. So that's a bit of a game to play. Luckily, there's a very, very convenient framework that helps you pick multiplication maps so that your product of your deformation of your deformed algebra is associative. The framework lies in homological algebra. In particular, this theory called Hochschild cohomology is used. It's very, very useful. So in this framework, the first multiplication map is a 2 cocycle. The second one is just a 2 cochain, if you're familiar with the language of homological algebra. And further, the first few Hochschild cohomology groups, these contain a lot of information about the original algebra A and its deformations. So for instance, the 0th Hochschild cohomology group, this could be identified with the center of A. So that's cool. Anyway, if you like this stuff, if you're even mildly curious, here's some references. There's a very, very, very nice article in the AMS Notices written by Sarah Witherspoon. And there she talks about deformation theory, Hochschild cohomology, and she highlighted work of Hochschild, of course, Jim Sashev, and also work of Murray Gerstenhaber, who just won the Still Prize for his contributions to this field and other fields. So if you're listening, Murray, congratulations. There's also a nice article by Gerstenhaber and Tony Gianquinto that, I mean, it delves more into the examples that we were discussing before. So if you're new, I mean, I would check out this article and this article. I think it's nice. And to end our story in deformation theory, I just wanted to highlight some work of my buddy Chris here. He's done tons of work in deformation theory. There's much more to come. As you can see, some of his work has appeared in fancy journals, Advances, Proceedings of the LMS. I mean, there's really cool stuff here. So check it out if you want to learn more. So that ends my story in deformation theory. All right. Three stories. Okay, last story will be on symmetries. I like symmetries. I like symmetries because you can draw pictures. Well, at least classically, you can draw pictures. Okay, so as was mentioned, when we think of a symmetry, it's a way of transforming an object back to itself. Mathematically, say that you're given an object X, a symmetry of X. This is a structure preserving transformation of X to itself. And often we want these transformations to be invertible. Now, classically, if we take an object X and collect all of its symmetries, this forms a group or a monoid if we don't care about invertibility. Now, the operation of the group is composition of symmetries, and the identity element of this group is just do nothing to X, just do nothing. So for example, if I take my parabola here, very nice shape, its collection of symmetries is the group Z2, consisting of the flip across the y-axis and do nothing symmetries. I can also take this star here, very symmetric object, where symmetries are really generated by rotating by 2 pi over 5 radians, and also flipping across some axis. And with this shape, we get the symmetry group, the dihedral group of order 10. Then, okay, yeah, circles are symmetric, very symmetric. So we get an infinite group here. And we can rotate by any degree and flip across any axis. And the collection of symmetries can be identified with the semi-direct product down here, so a non-abelian group. All right, so symmetries are great. The symmetries of geometric objects, they also go hand in hand with symmetries of their corresponding function algebras. So take, for example, if I take symmetries of C2, right, they're going to correspond to symmetries of the polynomial ring in two variables. So on the geometric side, linear invertible symmetries of C2 correspond to linear invertible maps that I have here going from C2 to itself. And on the algebraic side, linear invertible symmetries of the polynomial ring correspond to degree preserving automorphisms of the polynomial ring. And both of these collections of symmetries, they could be identified with the general linear group of invertible 2x2 matrices. Now, how do we get into noncommutative algebra? Well, the question that prompts this is, what about symmetries of deformed objects? Or more accurately, what about symmetries of deformed algebras? Now, ideally, when one deforms an algebra, its symmetry should come along for the ride. But we run into a snag when we stay within the framework of groups to capture symmetries. So let's see an example here. If I take the polynomial ring in two variables and I Q deform, okay, so I get this noncommutative algebra down here that we discussed before. Now let's take their symmetries. Now on one hand, for the polynomial ring, we pick up GL2C, as was just discussed. But as soon as I move away from Q equal to 1, the symmetry groups just jump around. They just jump around. Q equal to -1, I can only have diagonal or anti-diagonal matrices acting linearly. And as soon as you get away from Q equal to plus or minus 1, I can only have diagonal actions. So yeah, this is kind of weird. This is not ideal. We took an algebra and we continuously or smoothly deformed it, but its group of symmetries jumped around. So we need a framework larger than group actions, larger than group symmetries in order to handle symmetries of deformed objects. For instance, it would be nice if we could just deform a group, but groups, especially finite groups, they don't really deform. I mean, I can't take like a dihedral group and stick in a Q and get another group of the same order, for instance. So These days, folks think about symmetries in a broader sense, using algebraic objects that generalize groups, one being so-called Hopf algebras. And for this, it's really convenient to stick all of this in the language of category theory. I mean, trust me, it's very nice to use just one big enveloping theory to handle all of this. So really quickly, if you haven't seen category theory before, I highly recommend checking out Titan A. Bradley's site for some great chat on this stuff. She's very clear. But essentially, a category is a collection of objects and structure preserving maps between the objects, subject to nice conditions. So category vector spaces with linear maps, that's a category. Or collection of reps of a group or modules over a group algebra. This is a category where the maps are G maps or linear maps that intertwine with the group action. All right. So that's a category. Before a symmetry framework, we need a category to work in that is so-called monoidal. Now, what this means is that we have an operation that usually is called tensor that combines two objects of the category and spits out a third, and also combines two maps of the category and spits out a third. All right. For a monoidal category, we also need a distinguished object that plays the identity object or plays a role of the identity object with respect to this operation. So recall that monoids are sets with an operation that have an identity element. A monoidal category is just a categorification of a monoid. Some examples of monoidal categories are, category of vector spaces, where the tensor product is just tensoring over the field F, and the one is just the ground field F. And in this category, rep G, if I take the tensor product of two representations of a group G or of a group algebra, then I get another representation by using the diagonal action of the group. Further, what is the one? The one is the trivial module, where G acts trivially on the ground field C. All right. So this is our setting for symmetries. Now, in order to really capture them, I need to really tell you what an algebra is. So an algebra in a monoidal category, this is an object. And what we're going to do is we're going to equip it with a multiplication and a unit. So basically it's almost like you are mimicking the structure of a unital ring. All right. Oh my goodness. Okay, so the example you want to keep in mind for this is if you have the monoidal category of F vector spaces, an algebra in this monoidal category is just an F algebra. It's just a vector space equipped with a unital ring structure. Okay. If I have the monoidal category of, let's say, representations of a group, well, algebras in it are C algebras that where its collection of symmetries contains the group G. Okay, so it's an algebra where G acts on A, or G serves as a collection of symmetries or some symmetries of A, but A might have other symmetries out there, especially in a larger monoidal category. So this setup works very nicely for handling symmetries of deformed algebras as well. And the reason why is because Hopf algebras are considered to be deformed groups, and their category of representations is monoidal, and you could take algebras in it and then proceed with this generalized study of symmetry. Now to wrap up, I know I'm skipping a lot of detail here in this last part. I know I am, but I just wanted to give you a flavor of how symmetries work categorically these days. I think this stuff is pretty. If you want to know more, here's some books on the left-hand side. And also recently, some folks in the second Women in Noncommutative Algebra and Representation Theory workshop, we produced some work on algebras and so-called group theoretical fusion categories. And these are monoidal categories that are really conveniently classified by data from group theory. As you can see, there's Angela Dabiri and I, along with Yibi Morales. Julia Plavnak, Monica Mueller, and Anna Rose Camacho. It's a lot of fun. So that ends my story of symmetries. And I hope that you enjoyed this journey in noncommutative algebra. I mean, it's a very rich field. And I'm very grateful to the JMM for having, or JMM committee, for having 3 sessions on this subject this week. We're friendly folks, and I hope that you'll consider joining us in future adventures. Thank you very much for listening.
Awesome, awesome, awesome. Let's thank our speaker. Let's thank Chelsea Walton. Amazing, just amazing. If you get the opportunity to take a look at the chat, Chelsea, it's all just positive feedback about.
I'm just talking to myself up here.
We are blown away. It was an amazing talk. I know that we have to be very careful about time. So I think there will be 2 questions. There was one in the chat, and then I also see that, oh my gosh, my niece is trying to call me on FaceTime. I also see that Tarina has a question. So I'll let Tarina ask, and then I'll ask the question that was in the chat.
Okay.
I don't have a question.
Okay, hello.
Oh, sorry, your hand was raised.
Hello.
Sorry, your hand was raised. So I thought that meant it was a question, but maybe that was an excited hand clap. Okay, so the question in the chat, it came from, sorry, it really threw me off that my niece started calling me. From Isaac Langer, and he asks, can all algebras be deformed?
No.
Okay.
Well, trivially by leaving it alone. But there are, that's like Hochschild cohomology, what I was talking about. It also detects when the answer to that question is yes or no. Yeah. Awesome. Good question. Thank you. Yeah. Check out Sarah's book on this too. Sarah Witherspoon has a new book on this stuff. Yep.
Okay. I don't know if there are any other questions. I know we are close to time.
Okay.
Chelsea has gratefully given us her email, and I think she's speaking from experience, very open to talking to people about her work. So let's thank Chelsea once again.
Yeah, thank you. Thank you. I really appreciate it.